So first thing is, I told you I had your quiz. I tried, I really did. And it's not like I didn't have time. It just took such a tremendous act of willpower yesterday after staying in the stream all day to even get your quizzes out. And it started well enough, you know, and it's like, okay, good, yeah, I can take that, yeah, okay. And then, you know, as it goes on, you know, you reach your feet and start to get you a little depressed. And then you just start, like, not being able to even think anymore. And, you know, start going like, boy, if I don't stop, I'm either just going to get, well, I don't know. Anyway, I reached that I don't know point at some point last night. Then I thought I would get it this morning, you know, but then that alarm went off and, man. I said to myself again, man, I think I've got the feeling back in my toes, but I'm not sure. I think I do, but I don't know if I should. Anyway, I'm sorry. So, I'm trying to forgive myself. I hope you will also forgive me for not having those at this point. Like I said, I got them mostly done, but I'm not going to give them some of them back. That's just not cool. I thought it would be, I think it's probably useful to talk just a little bit about one of the issues I found with your responses to the quizzes from last time. So fundamentally, we were looking at a problem, and let's just draw up that valley cross section, because I think that's where if you didn't step through the thought experiment when you did the quiz, you might have gotten the right answer, but probably not for the right reason. So the cross section you were call looked something like this. And down here we had our valley bottom, where presumably, you know, we've got our columnar basalts. There's joint blocks down there. And right up here, about this elevation, was our boulder bar. And we had about, I think it was 70 meters of relief between the two. So that is, that would, that was 70 meters from the bottom of that gorge, that bedrock valley bottom, up to this boulder bar. And I asked you a couple of questions. I said, okay, well, what's the depth of flow for initiation of motion of the particles on this boulder bar up here? And we came up with that we would need a depth of flow, and it's not, I'd have to exaggerate it even to draw it on here as anything but an overlapping line, but you know, we came up with a depth here, and people pretty much almost all got this one right. This was 8.1 meters here for initiation of motion of the particles on that bar, which were, I think the median size I asked you about was 15 centimeters or 0.15 meters. Does that sound right? And then down here we had, you know, can we rip out the bedrock, which has a maximum joint spacing of 0.83 meters, I believe. And here we needed, in order to just move those blocks, never mind rip them out of wherever they were, but you know, just to mobilize a block with that fundamental dimension was 41, 42 meters. 41 or 41.5 or 41.44 or something, so say 40 meters, round it off. So I'll draw that in here. So that, so if we drew that in, where we're asking the question, right, about motion of these blocks. With that D max 0.83 meter, that's all these decimal places. Okay, let's just say, so less than a meter. Up here we've got about 8 meters of flow in order to mobilize boulders with a median grain size of 0.15 meters. And my question after I asked you, okay, what are these two depths of flow, this 8 meters up here and this 40-something meters over here, was can I have a flow which is simultaneous, can I have an event, a flood, ripping down Moses Coulee that is simultaneously ripping bedrock out here while depositing boulders up here? I got a variety of answers, but I'm not sure anybody really quite visualized it the way I was hoping you would. So let's just step through that question. Okay, so for for just barely moving the stuff down here, I need at least 40 meters of flow. To just barely mobilize stuff up here, I need about 8 meters of flow. So let's start with that. If I'm just barely moving this, and I might be depositing, and so I could, it's somewhat naive and simplified to just extrapolate this level over here, but that's the easiest thing to do. And so that says, since this 70 meters was between the base here, that this depth of flow then relative, so a depth of flow of 8 meters here would correspond to a depth of flow of 78 meters here. And it's just the simplest of geometries, right? Just extrapolating a straight line across from what would we suppose be about the sort of flow that would typically deposit a boulder bar. That is, maybe the flow might be a little greater, a little less, a little deeper, a little shallower, whatever, but around there. And if I have 78 meters of flow depth above this valley bottom, well, now that sounds pretty damn ample. That sounds pretty good in terms of if my objective as a Missoula flood, my goal in life is to rip out Moses Coulee, right? To tear out these blocks down here, and now I've got nearly twice the depth that I might need to mobilize those blocks down there. And so if I just do that thought experiment and look at that, it's like, well, yeah, I could, if I had the flow that was just sort of mobile, where the boulders on that bar were just mobile, I have ample shear stress to tear out blocks down here. So yeah, I could be depositing up here and shredding down here. And that's all there is to that question. I didn't see that answer very much, but like I said, I didn't get through all the quizzes. Maybe somebody didn't get to that. I got a lot of, I got some answers like, yes, because with hands. It's not just you, Brenda. I can respect that, it's quite, perhaps when you're trying to get a quiz done on Sunday night, you're not maybe up for sitting down and calmly thinking through a thought experiment. I get that. That's why it's my job to kind of try to step through that process with you a little bit. Hey, Brenda, yeah?
So I think part C of this question was if you filled it all the way to the brim. Could you see the same?
So that was after I asked could you simultaneously deposit up here and shred down here? There was also if I because there are some recognizable high water marks way up here. They're right there on that seam. So, and part of the point of the paper out of which I drew this, because this came out of a Nature paper a couple of years ago, part of their point was simply, well, I think they were partly coming at it from a Martian point of view, planetary science point of view, where if I'm looking at something like Valles, if I'm looking at these valleys on Mars, and I'm trying to figure out what kind of events could have led to the sorts of flows that would carve those valleys, I guess the typical thing that the planetary scientists, and it's interesting, that it's a relatively primitive sort of thing to say, oh, the flow that carves that canyon is the one that fills into the top. Which isn't necessarily the case at all, right? I mean, if I've got 78 meters of flow here, it's pretty likely I'm going to be ripping down into that bedrock there. There's no way that I need to fill it all the way up to the top. And that was essentially the point of the paper. It ticked off some people who do Missoula floods because they said, well, we never said that. And it's like, yeah, I know you never said that. It's still an interesting thought experiment. Even if they had to sort of like overdo if they had to sort of straw man the Missoula flood people in order to get a paper published in Nature. Whatever. Nature likes that kind of thing, I guess. Anyway, what they were saying was, well, you don't need to, for those canyons on Mars, it's ridiculous. You don't need to fill them up to the top, just like you don't need to fill this up to here in order to carve that canyon bottom. Now, so that second part of the question was, well, if this were the level of the last flood to go through Moses Coulee, is it likely that I would be depositing here while scouring here? And if I filled it up to here, I'd have, as somebody pointed out I'd have like 70 more meters or 75 more meters of flow above that bar. Plenty unlikely that I'm going to be sort of casually laying down 15 centimeter boulders in deposition. It's vaguely possible because deposition versus erosion isn't just about thresholds. It's also about gradients and transport capacity. Still, if it just doesn't seem awfully likely. It seems, if anything, if I had flows that big and I were somehow depositing somewhere, it seems like the pieces I would be depositing would be a lot bigger, or would at least include particles a lot bigger. So, you can get as sophisticated as you want with the reasoning. Point was simply like, yeah, if I've got 150 meters of flow depth over this point, chances are I'm going to be scouring the hell out of that. But I'm also going to have like 75 meters of flow depth above this point. Chances are I'm going to be scouring the heck out of that too. So it doesn't seem awfully likely that a flow that filled this to the very top would leave behind the kind of morphology that we see, and that's the short end. And where they went with this in terms of the Martian case was to say, people have sort of puzzled over how could you possibly, people have thought that the mechanism for generating the flows on Mars was groundwater. Sort of a sudden release of groundwater, as sudden as groundwater can ever be. But part of the problem is that groundwater can only ever be so sudden, right? It's groundwater. It still has to flow through the subsurface. You can't generate a valley, a canyon filling flow that way. And their point was simple, you don't have to, that's silly. Well, I didn't just say that's silly, because of course, nobody ever says that in a scientific paper, but essentially, that's silly. You don't need, all you need is enough to actually tear at the bedrock. And then, this flow or this flow can simply deepen that canyon. Why would you, it's almost like, well, why would you even think that you had to fill it up to the top? And in the case of Moses Coulee, again, there is a high water mark somewhere up here that is, I can't remember if they say in the paper exactly how they identify it. but it's kind of unimportant. Okay, so say there is a high water mark up here. Well, the point is there was more than one Missoula flood. I mean, in fact, there were maybe 50 or 100 of them. Now, it turns out Moses Coulee is a bit of a, among all the channels in the channeled scablands of eastern Washington, Moses Coulee probably didn't have all that many. Moses Coulee probably had far fewer Missoula floods go down it than the other places in eastern Washington. And okay, that's fine. That still probably means there was more than one. And even if there were only one, we don't really have a good handle on how long it takes for a Missoula flood type flow to rip out a canyon. You know, it's hard to do the experiment. But point being, well, you know, all you gotta, if I've got flow of some duration, it could, you know, if I start up here, or even if I start with some, you know, just minor, you know, sort of subtle topography up here, which is probably some, you know, the initial case was not much in the way of relief. But what we know from the way flows work is you start to deepen something and then you start to deepen it faster because now you've concentrated flow wherever you're deepening. And so, you know, again, I don't know how many floods and how long it would take to tear out, you know, from all the way up here all the way down here. But that's another question, I guess. Just because I've got a high water mark up here, all they're saying really is a high water mark up here doesn't mean that the last time there was Missoula flood peak flow through there, that's where the high water mark was. And the thing is that, you know, you only keep the high water marks that don't get erased or that are left in ways that are visible. And in some sense, you know, like if I've got something like a vertical canyon wall, typically don't really leave anything like an observable high water mark there. There's no place to put a backwater except something like over here. So in a sense, that boulder bar, even though it is boulders, well, it's something like a backwater deposit that one of the ways we figure out how deep paleofloods are is we look for deposits that are associated with those floods, and we go, well, the water was at least this high, and in this case we go, well, boulders, okay, you know, typical paleoflood stuff, we're looking at pretty fine deposits in these backwaters where we're looking at trying to figure out how deep the flow was. You know, relative to the size of relative to how big we think the Missoula floods were, you know, a 15 centimeter rock isn't that big. So this is something like a backwater deposit that we can say, well, now it's not necessarily the case that, again, just like where an observation of a high water mark up here doesn't mean that the last flood was that high. It's also true that just because we have something like a high water mark here, that doesn't mean that the last flood was that high. But it is still reasonable to say, well, would a flow that could tear out blocks here also deposit up here? And yeah, actually that seems kind of reasonable. Because again, that 40 meters is just to barely get into that initiation of motion. If we get up to like a 78 meter depth, we're getting up, you know, high enough. We're getting actually to, okay, if I were to go ahead and calculate what the Shields number was for this depth of flow, it comes out to about 0.05, which turns out to be about the same as the average Shields number for bank full flow in gravel bed streams. Oh. Well, that's interesting. So we've got essentially, that's like bank full flow, which is essentially, we think, well, okay, at about that 0.05, 0.06, something like that Shields number, we would have not just sort of partial sporadic mobility, we would have general mobility of the particles on the bed. And that is, things would really be ripping. Instead of just sort of occasionally, sort of watching for something to, oh, yep, it moved, okay. And that's where we are at the 40 meters, at the 0.03. That's the, yeah, I think it moved, yep. Come here, did it move? Yep, okay, cool, right? When we get up, when we, go up that high, we're, yeah, that's all moving, no doubt. Okay. Any questions on that one? Yeah, again, while I feel it's my job to teach you how to do these sorts of thought experiments. That doesn't mean that I think any the less of you as people, because you couldn't on a Sunday evening. Yes?
Is it possible that in a flow like that, you could erode down more than 8 meters to the point where the flow would stop on the boulder bar?
Oh, so you're saying, like, could I have, during an event, say, started off high enough and then lowered the flow such that now all of a sudden I get deposition up here? Is that?
Yeah.
Yeah, certainly. And, if we're going to get a little bit complicated about how this actually worked, this cross-section here is a bit fake, sort of, because it's kind of looks a little bit arbitrary. But what they also showed in the same figure, and that I included in your quiz figure, was a map of the Moses Coulee little area there with colors on it according to their modeled shear stresses. And essentially, not far upstream of this point where the cross section looked like a major nick point, or maybe the major nick point, or at least a major nick point in Moses Coulee, where they had particularly high shear stresses and an abrupt drop, essentially a steep point in that valley floor. And so it's not only possible, it's likely that maybe that last flood, well, clearly the last flood left the nick point at that point. It didn't get past that point, but that nick point had already ripped upstream of this cross section. And so it is quite possible that you had general movement of stuff through here, then that nick point moved through and that dropped the water level and caused deposition up here. So yeah, that's actually not only possible, but quite plausible. I think what you said. Any other questions? Okay. Let me just see. I thought there might have been something about. Okay. I was asking for a similar bit of thought, sort of a similar kind of thought experiment in question number 4 in the quiz you just turned in. And that had to do with, and I want to continue talking about detachment-limited channels or channel profiles in general today. But on the subject of thought experiments and, okay, so here's the problem. We have a profile that looks something like, get this right. All right, so that is, we have 3 sections of the stream where we see concave stream profiles. And this one is marked as having a limestone rib. And we also know there's a a fault right here. So even just looking at that, we go, huh, what's up with that? You know, obviously this place is steeper. If we actually look at the plot of, the log plot of log area, contributing area on the x-axis and log slope on the y-axis, we get something like that. That is we've got points for this part here, for this part here, and then in the middle, the slopes jump up. And I talked last time about the fact that particularly the detachment-limited erosion model predicts that I would have this sort of function between slope and contributing area. Because if we solved it for the equation for conditions at steady state where uplift balances erosion, and then we solve for slope, we see that slope is expected to be a power law of contributing area, and because m and n are constant, it's going to be a power law declining like that. And by power law, I just mean if I plot it on log space, it forms a straight line. And what the authors of this paper did in looking at this particular spot was to see, this is kind of interesting what's going on here. We can see it pretty clearly on the long profile. It pops out even more clearly as a bump in this slope area profile. And if we fit sort of lines with the same slope to these three places, we get this one is coming out steeper. And the steepness part of this, in general, what we mean is this coefficient here, right? Because this, in terms of fitting a line here, that line is often represented like so. And it's pretty straightforward to go, oh yeah, well, okay, if this is a detachment-limited stream at something like close to steady state, then theta is the ratio of these exponents m and n, and the steep, what we call it, and we'll call this theta a concavity, and this k sub s, which we'll call a steepness, is going to be this bit here. So if k sub s is larger, because it is larger here than it is in the other two places, we've got one of a couple of obvious sorts of answers, or one or both of a couple of obvious sorts of answers as to why that place is steeper pop out. That is, if k sub s equals this bit, and we've got differences in k sub s, then we've got differences in uplift rate or erosion efficiency. And so I think a couple of the questions I asked were simply like, okay, let's assume that the uplift rate is constant everywhere. That is, we're not dealing with a case of chain of different uplift rates. Then what must be different? Well, what must be different is k. And what we see from that is that, okay, if k is smaller, then k sub s is larger. And if K is smaller, that's what we would expect for harder, more resistant rock, which might correspond to something that we would call a rib lithologically. That is, if I'm out in the field and I notice a geologic feature and I'm calling it a rib, it's probably because it tends to kind of stick out and be more resistant than the rest of the landscape. And the fact that it's limestone is sort of beside the point. Limestone could be anything from that crumbly crap that they call limestone in Florida to pretty hard crystalline rock. Okay, so, all right. Now, then the other part of it was, okay, well, let's assume that that's not the answer. Let's say, you know, given that the erosion efficiency is the same everywhere, what might be the issue? What might be causing the greater steepness here? And again, we go, okay, well, if that's constant, then the only other thing I can vary other than n, and let's just assume that's constant too, then the only other thing I could be varying would be the uplift rate. And you know, there is a fault here. Now, it does say something about, well, the profile is smooth through the fault. It's like, no, that, you know, that perhaps that's evidence against there being a high uplift rate here as the cause of that. But, you know, we don't even need to, you know, that wasn't really the question. The question was simply, okay, if all else is constant except for uplift rate, then that's kind of what's left. That, you know, perhaps we have just a place here, you know, where this bit is going up faster than the places around it. That would mean that, you know, let's just think about what that means. Well, in terms of the way we set up the mass balance, very simply was, well, I've got uplift bringing rocks in, and I've got erosion taking them out. If they're coming in faster, then if I've got the same flow to work with, then I'd have to get steeper to do that, to carry those out. And that's, you know, that could be what we're seeing here if other evidence, you know, and we have to look at other evidence, such as, well, there is a fault here, is it in the right place, you know, is that consistent with where we see the differences in slope and so on. So we, you know, obviously there'd be other things that we would want to look at in order to conclude that it was an uplift thing. But again, the question was simply was more simple than that. Just like, okay, you know, well, given this is not the variable thing, then what could be the difference between these two places? Is that reasonably clear, having spoken through it? I obviously haven't looked at your answers yet, so I don't know how clear that was to you last night or the next.
Yeah.
What's that?
So it makes a lot more sense now.
Okay. Well, I'm glad it makes sense now. Obviously wish it had made sense last night.
It was just like more simple for me.
Yeah.
I overthought it.
Yeah. You know, it's when I have like ample time to just speak and speak, I make things more clear. But I know your patience when I write quiz questions is limited. I'm not going to write a page long. Yeah.
So what is K? It's erosion efficiency.
Well, there is a lot of stuff sort of piled into K. So I call it just generically erosion efficiency. But it is worth thinking a bit about what all is in there. So, and that's some of what I wanted to try to talk about today. So let's just go there.
Can I ask a question?
Yeah, of course. Yeah, before I go there, right.
What are M and N? Like, I know they're constants, but where do we actually get those values from?
Well, we can go there too. Okay. So, yes, let's go there. So, all right. You ready for this? Let's start with a simple statement of what shear stress is for uniform steady flow. Okay, and I think pretty much I hope all of you recognize that sort of expression. Flow depth, slope. This S would be the same slope we're talking about over here. Okay, let's say that erosion rate might be proportional to shear stress to a power. And I put a prime on that K because I've used a plain vanilla K over there, and I don't want to imply that it's the same one. And, you know, don't know exactly, and that's just kind of a way of saying, well, I think erosion rate's probably proportional-ish to shear stress. Maybe it's not linear because, you know, transport laws tend to have tau to the 3/2, so, you know, maybe it's something like that. But, you know, let's say for starters, let's just leave off that P, okay, just to make things slightly simpler. And we can put it back later if we want. All right, now my issue is that if I'm looking at topography writ large, there are some things that are relatively easy to calculate or straightforward to calculate and others that are not. Contributing area, slope, I can calculate those based on a topography. Flow depth, not so much. All right. Well, I've got other options though. I mean, if I'm talking uniform steady flow, I've got some decent empirical formulas that describe flow depth as a function of other variables, including the Manning equation, which says that flow velocity is a function of flow depth, slope, and a Manning roughness coefficient. And if it looks like kind of a screwy equation, yeah, it's kind of screwy. I mean, but that it seems to do well. So, all right. Well, that got me maybe somewhere, but now I've got flow velocity instead of depth. That didn't necessarily do me the kind of good that I might hope for. But let's see, if I think a bit about what I would like to be able to say, get this equation in terms of, say, contributing area and slope. Well, discharge, you know, contributing area is sort of at least on some level, I figure is going to be a proxy for discharge. So can I get discharge out of this? Or if I want discharge, and I've got, okay. Discharge is most simply written down in terms of just a conservation law. I mean, this is simply conservation of mass to say that discharge is the average velocity times the flow depth times the flow width. Okay, cross-sectional area times velocity, that's discharge in terms of volume per time. Okay, well, at least if I can get rid of a variable this way, I can get rid of so I can say, all right, well, Q, can make the substitution of this for U. H to the 2/3 times H is going to give me H to the 5/3. Got H to the 5/3, still got slope to the 1/2, still got Manning N, and then I got to throw in the flow width there. Boy, flow width is a bugaboo, isn't it? Yeah, I don't have a simple formula for that. All right. Well, okay, I lie. I do because I'm about to give you one. But you know, I don't have a nice first principles formula for W. So I got to go with something that I kind of kludge from data. And typically, we observe something like W is, let me just, you know, as long as I'm using K's for stuff, W is, let's say, proportional to Q to the 1/2. And that's just based on a lot of data. Is it always true? No, of course not. So if we wanted to be, I'll leave it as numbers for now, because numbers are a bit more real than when I start sticking in variables. But you know, it doesn't have to be a half. I could put in a different, more general thing there. Just like I've got a general variable there, I could have something general there. But let's just go with that for now. All right. Let's see then. If I Q, I just go back to my discharge equation here, then plug in my value for W, and I've got h to the 5/3 slope to the 1/2 over n times kW discharge to the 1/2. All right, let me just divide both sides by Q to the 1/2. Cancels over here, and so I've got, right, see what I did there? Okay, so I've got Q to the 1/2 equals h to the 5/3 slope to the 1/2 over n and k sub w. Did I get that right? I think that's right. What was the point? Oh yeah, the point was I want something other than h flow depth here. And now I've got a function of things that I kind of want. Because I'm feeling kind of confident, especially based on some of the data, peak flow versus contributing area that I showed you in the quiz and in class last week, that I can use contributing area for discharge. But so I can solve this for the depth. Okay, and it's not going to be awfully pretty, but it's going to be functional. All right, so let's say then I've got h to the 5/3 equal to Q to the 1/2 over k sub w times n up here divided by slope to the 1/2. Did I catch everything there? Oh, yeah, I think that's, just count. 1, 2, 3, 4, 5 variables there. 1, 2, 3, 4, 5. Good, awesome, 5, 5. All right. And then, again, I didn't say it was going to be pretty. Raise both of these to the 3/5 power. 3/5 cancels my 5/3 there, and that's as good as I really need to get over there. Yeah.
So when you divided both sides by Q to the 1/2, on the left side, why did you cross out the bottom 1/2?
So, yeah, let me just show you. So, if I've got Q over Q to the 1/2, that's equal to Q to the 1 minus 1/2.
Oh, got it.
Okay? Okay. So there's something I can put in here for H. Let me just go continue backwards here. Leave that stuff up for now, but moving backwards across the board here. And go, okay. Again, this is getting ugly. And I never promised you a rose garden, did I? Okay, so now I can say that my shear stress equals density. And I should be specific because I've been trying to be generally. That I'm talking about density of water, gravity, of course, and now I've got this bit of a monstrosity to plug in here. I've got a discharge to the 3/5 times 1/2 is 3/10. I've got n to the 3/5. Or should have left myself more room. I've got kW to the 3/5 and slope to the also 3/10 in the denominator, but another slope up here, so 1 minus, so my result is let me just write, slope to the 3/10 down here, and slope up here, which, let's try to do some semblance of tidying here and put sort of constant-ish things into a group over here. And Q to the 3/10 slope to the 1 minus 3/10 or 7/10. You asked. Okay. I suppose I could have just waved my hands, but it's not in my nature. So, all right. That still doesn't tell me how I get particular values or whatnot on contributing area. But I did see last time, you know, in plotting up for, say, the Ozarks and Puget Sound streams, that that mean annual flood magnitude was proportional to something like contributing area to the 0.6 to 0.9 in there. So let's say 0.8, just to actually have a number. So if I continue my backward migration here, I can say, let's say contributing area, or I mean, let's say discharge is a function of contributing area. And again, I'll go ahead and put in a value here, but again, you know, we could make that a variable, but then just to sort of make it a bit real, let's go with a number for now. Okay, which means if I plug that into there, I get shear stress. Let me try to go ahead and pre-neaten here just a bit. My KQ is going to be to the 3/10, so I'll bundle that in with the rest of stuff here. And this would be contributing area to the 0.3 times 0.8. Oh, golly. Okay, so 0.24. And still slope to the 0.7. And now I've got shear stress as a function of other things, including contributing area and slope. So if I just wanted to stop there and say that maybe the only other thing I want to do is say, okay, shear stress is this, erosion is proportional to shear stress. where K prime here is, I say, a purely lithologic thing. So let's just keep it K prime for some sake. So now I can write again, if I just take that erosion is proportional to shear stress with this K prime character, then I end up with this. Bit of a monstrosity, yes. And how can I possibly have any confidence that I didn't just totally flub some major aspect of what I'm trying to do here? It's because I've done this a few times. Sorry for going over, but there's our answer. What are M and N? Well, if I think that erosion is proportional to shear stress, M is 0.24 and N is 0.7. What's K? Well, it's got a lithologic component, it's got a roughness component, it's got a how big are my floods component, which has to do with my flow regime, my precipitation regime, and even just how flashy is my drainage basin. Am I talking spongy high cascades or steep shallow soils in the coast range? And then this K sub W, which is essentially just the, how wide are my channels, which is probably, if I'm talking about a detachment-limited system, may also be a lithologic thing. So I've got at least a couple of terms that relate to lithology. I've got some terms that relate to hydrology. And if I think that it's a different function for erosion, then my powers would be different. But that's how we get there from here. Yeah. So you will actually get to play with this sort of model in your labs today. Both the detachment-limited version and a transport-limited version. I'll warn you, what you will find is that the transport-limited version is really finicky about your time steps because it's a finicky sort of thing. And I didn't necessarily mean to do this, Derek. I was going to actually totally avoid doing this for you, but gosh, you guys asked. What I was going to talk about today wasn't really all that much better than this anyway, or maybe wasn't any.
I understood the last part.
All right, have a great beginning of your short week. Start going along. See you.